let's go back to the ones where we do have a picture of the graphs, like in number 1, and talk about what the derivative can tell us. Well, first, let's remember what derivative means. Graphically, slope of the tangent line. So let's look at the slope. When the function is increasing, like here, if I draw a tangent line and estimate its slope, I can only estimate positive numbers. The slope is positive. So a function is increasing on an interval when the derivative, the slope, is positive. On the other hand, when it's decreasing, if I draw a tangent line, the slope is negative. So here, the slope is negative, the derivative is negative. That tells us a function is decreasing on an interval. So that's how we're going to use the derivative to tell increasing or decreasing. Now, how about for relative maxes? Well, here's a relative max. What's the derivative there? If I draw a tangent line, the derivative is 0. Here's a relative max. I can't draw a tangent line. It's pointy. Here, the derivative does not exist. But it's a relative max, not because it's pointy, not because the slope is 0, but because the derivative changes from positive to negative. If the function has a positive derivative, we know the function will be increasing. If the function has a negative derivative, we know the function will be decreasing. If the function changes from increasing to decreasing, we know there has to be a relative max. Similarly, at a relative min, what was the derivative before? Well, the derivative, or the slope, is negative. The derivative after, or the slope after, is positive. So when the derivative changes from negative to positive, we get a relative min. Sure, at that point, we know the derivative isn't positive or negative. In this case, the derivative is 0, because the tangent line had a slope of 0. But that's where we start. We find the critical numbers where the derivative is 0, where the derivative doesn't exist. Then we figure out what's happening to the left and to the right, so that we figure out, was the function decreasing then increasing, or increasing then decreasing? So here's how we use the first derivative to test for increasing or decreasing. If f prime of x is greater than 0 for all x in the interval a to b, then f, notice it's f, is increasing on that interval a to b. If f prime of x is less than 0 for all x in the interval a to b, then f is decreasing on that interval. And if f prime of x equals 0 for all x in that interval a to b, then f is constant on that interval. So greater than 0, that means f prime is positive. It tells us f is increasing. So it's really important that we don't ever use the word it. We have to specify what is it that we're talking about. F prime is positive, f is increasing. And it's important that we distinguish between something being a positive value and something increasing. That's not the same thing. Positive values, we know what those are. Increasing literally means going up. This is moving in a direction. This is a type of value. And then we know how to use that to determine relative extrema from looking at the graph. So the first derivative test to find relative extrema. Let C be a critical number of a function f. If f prime changes from negative, so it's f prime that we're regarding, is changing from negative to positive at that critical number C, then f has a relative minimum at that critical number and its y value. We know the relative minimum is the y value. So f prime changes from negative to positive. Think about what that looks like. F prime is negative, which means f will be going down, and then f prime changing to positive means f will be going up. So we have a change from a negative to positive, and something is happening, something critical is happening, like the derivative is 0 or does not exist. Then we have a relative minimum because we have a valley. If f prime changes from positive to negative at that critical number, then f has a relative maximum. So f prime is positive, means f goes up. Then f prime is negative, means f comes back down. So what's happening at that critical number has to be a hill, so we have a relative maximum. Identify the open intervals on which the function is increasing, decreasing, and find any relative extrema. So remember step 1, find the critical numbers. Use the derivative to do that. You should already have the derivative on your paper. G prime of x equals 3x squared minus 3x. Remember how we find a critical number. Take our derivative, where does it equal 0, where does it not exist? There is only setting it equal to 0 in this. There's no denominator here. So where does it equal 0? Let's factor. And we get two critical numbers, x equals 0 and x equals 1. These are our critical numbers. If we look back into the function, 0 and 1, they're both defined there, so they are our critical numbers. Next, set up our number line. Draw your number line, put on our number line the critical numbers and any domain restrictions. Polynomial, no domain restrictions. So 0 and 1, these are our x values. Next, find the sign of f prime, find the sign of the derivative on each interval. So f prime on this first interval. Well, how do I tell what it is on an interval? Just like we did in the picture, let's look back. We picked one spot, a representative spot, and we drew a tangent line, and we saw that that tangent line has a positive slope. Anywhere I draw it, though, would have a positive slope until it stops moving up. Well, similarly, we're going to pick a representative spot on our interval. Anything you want before 0. Well, you could pick -1,000,000. It's before 0, but is it easy to work with? No. Let's pick something easy to work with, maybe like -1. Plugging in our representative test value, we could plug it back in to the, oh, and I wrote f prime here, but we're working with g, so let's be consistent. Let's call that g prime. We're plugging it back into the derivative to see is it positive or negative. I don't care what value it is, so the easiest place to plug it in is into the factored form. This is why. We're going to think to ourselves, 3 times -1. What kind of number is it? Not what number is it, what kind of number? It is a negative. -1 minus 1, what kind of number is it? It is a negative. And what is a negative times a negative? A positive. So g prime is positive on that interval. Pick something representative between 0 and 1, like 1/2. Plug our test value in here and ask what kind of value do we get? 3 times 1/2 is a positive number. 1/2 in here is a negative, so a positive times a negative. Now it makes a negative. Test something to the right of 1, like 2, like 5, like 10, it doesn't really matter. 2 plugged in is positive, 2 plugged in is positive, and a positive times a positive is a positive. That's the fastest way to do it. We don't care the values, we care if they're positive or negative. So now I'm going to give myself a visual. When the derivative is positive, when g prime is positive, g is going up, increasing. When g prime is negative, g is decreasing. When g prime is positive, g is increasing. So now I can answer the question, identify the open intervals where the function is increasing or decreasing. Here's how I answer the question. G is increasing on -infinity to 0, but then again from 1 to infinity, so union 1 to infinity. I cannot just say, oh, look at my graph on the number line, because those are just notes for me. I have to explain what it is that I saw. So here's what I saw. Because g prime is greater than 0. That's why g is increasing. I saw that the derivative of g is positive. Similarly, g is decreasing on the interval 0 to 1. I can see that here. But I have to tell why. Because g prime is less than 0. So I did the increasing and decreasing part. Now I want to talk about the relative extrema. Well, if the function g is changing from increasing to decreasing, there has to be a relative max. If the function g is changing from decreasing to increasing, down then up, there has to be a relative min. Well, I know where they're located. They're located at 0 and 1, but what are they? That's the plugging in part. So g, our function right here, tells us the y value when we plug in our x value. So g of 0 is 0 cubed minus 3/2 times 0 squared. That looks like 0. G of 1 is 1 cubed minus 3/2 times 1 squared. Let's evaluate that, and we get -1/2. So it looks like we have a relative max at 0. So I'm going to say G has a relative max. The max is the y value, and the y value is 0. So the relative max of 0 at x equals 0. And then I have to use my derivatives to tell why, because G prime changes, the derivative is changing, the derivative changes from positive to negative. And here at x equals 1, there is a relative min because G changes from decreasing to increasing. So we will say G has a relative minimum of -1/2 at x equals 1 because, and again we're going to use G prime to say why we know that. G prime, the derivative of G, changes. G prime changes negative to positive. So it's important to remember that our answer is not this number line. Our answer is over here, how we write the description using the derivative to justify. Why don't you pause the video, try some of these next ones on your own, come back and see how you did. What I'm going to do now is I'm going to just show you the results of what's going to happen when we see different things from our number line. So I gave you problems specifically that give us a different kind of number line. So just to breeze through a couple of the main things that you should be finding. In the second one, we have our derivative, setting it equal to 0. So h prime equals 0 gives us the critical numbers 0 and 3. Your number line will look like this, 0, 3. Those are our x values. When you plug in test values like -1, like 1, like 5, representative values into our derivative, you get negative, negative, positive. I just want to point out that you're not always going to have it switching back and forth like the previous one, positive, negative, positive. It does not have to do that. Here, negative, negative, positive. But how do we answer our question of what is happening to the function? Well, we see h because it's negative derivative will go down, down again, and then up. Decreasing, decreasing, increasing. How do we say how the function is increasing or decreasing? So increasing, there's only one interval we have to worry about. H is increasing on the interval from 3 to infinity because h prime is greater than 0. How about where h is decreasing? Well, 0 is a value that is in the domain of the function. H of 0 exists. Since it exists, our function is probably just doing something like this. Decreasing for an instant has a 0 slope, then keeps decreasing. But the function is always decreasing. So we're not going to stop our interval at 0. We're going to say h is decreasing through that value of 0. Negative infinity all the way up to 3. Don't stop there because h prime is, oh, not greater, less than 0. Here we have going decreasing to increasing, so we know there's going to be a relative min at that other point. So h has a relative min of, now I didn't calculate it yet, so I want to do that at 3. H of 3 is 3 to the 4th minus 4 times 3 cubed. Plugging in 3, it looks like I get negative 27. So it's the relative min of negative 27, and it's located at x equals 3 because h prime changes from negative to positive. For the derivative we're using, g prime, is negative of 2x plus 2 over x squared plus 2x quantity squared. Now what's different about this one is how we're going to set up our number line. We get critical numbers from the derivative equaling 0. The derivative has no places where it doesn't exist since, oh no, it does have a couple places where it doesn't exist, but let's do the 0 first. So the 0 is when the numerator equals 0, and that is when x equals -1. G prime doesn't exist when the denominator equals 0, and that is at -2 and 0. The only thing is we're not going to call these critical numbers because if you look back to our original function, our denominator of our original function equals 0 when x equals -2 and 0. These are asymptotes, vertical asymptotes. So they are going to go on our number line because remember domain restrictions go on our number line and critical numbers go on our number line. These are the domain restrictions, this one and this one, domain restrictions. Okay, well this one is a critical number. So let's keep that clear because there's not going to be any maxes or min at a domain restriction, only possibly at a critical number. So here when we evaluate the sign of our derivative, we get plus, plus, minus, minus, but the only place we can look to see if there's a relative max or min is at this critical number. So we do have increasing, increasing, decreasing, decreasing, but this is the only place where we have a relative max because there's only a critical number here. So we could only, for the relative max part, say there's a relative max, plug in the -1, so g of -1, you get -1. So the relative max is -1 at x equals -1, because g prime changes from positive to negative. Of course, we can also do our intervals. Now, here is a big thing I want to point out. Increasing interval, increasing interval. Earlier, when we saw something like that, in number 2, 2 decreasing intervals in a row, and we combined it. We went from 0 all the way through, or sorry, -infinity through 0 all the way to 3. That entire interval all the way. We did not stop because 0 is in the domain of the function. However, this time, -2, not in the domain. This is a vertical asymptote here. Also, this is a vertical asymptote here. Vertical asymptote, vertical asymptote. We have to break where the vertical asymptote breaks. So we don't say g is increasing all the way through to -1. We have to split it up on 2 intervals, -infinity to -2, union -2 to -1, because g prime is greater than 0. Similarly, g is decreasing. We have to break it up because of the vertical asymptote from -1 to 0, union from 0 to infinity because g prime is less than 0. Notice that big difference.